Okay, so today we are going to talk more about regression. Sorry, let me move my slides up. Okay, today is going to be a kind of mixture. We're going to introduce a couple new concepts. We're going to introduce multiple regression. We're going to introduce interactions within a regression model. And then we're going to spend most of the rest of the time practicing model building. So we're going to do a lot of hands-on work coding today. Before we do that, I want to introduce two more concepts with how we handle the right-hand side of the model. So typically when I say the left-hand side of the model, I mean the outcome, the thing that we are building a model of, right? And when I say we're building a model of something, I mean that quite literally. We are building a mathematical model of how a process works, right? And we're saying this process works according to a line. If we're using linear regression, we're saying the process that determines our outcome, in this case, for your homework, you looked at attitudes about intimate partner violence. We're saying the process that determines intimate partner violence is a line that's a function of whatever predictors we include in the model, right? So we're literally, think of this like building Legos, right? We're building an abstract world. We're building a mathematical model to explain a real process, right? And I think when we say model, we should think of it quite literally, right? We're building an abstract representation of a real system, right? And it's always a simplification. A model is always simpler than the reality, and we know that, right? So do not mistake a good model for the real social process, right? Never make that mistake. Our models are not real. They're mathematical abstractions of a real process, right? We're not physicists who can actually just build out very precise, theoretically driven models of how a process actually works, right? We are not doing that. We are building prediction engines, but they are these little abstract toys that can generate insights about reality, right? There's a sort of canonical adage in statistics: all models are wrong, some are useful, right? I want you to always preserve that in the back of your head. When we build a model, we are not uncovering truth. We are designing an abstracted simplification of reality that can help us with insights, that can help give us insights into real processes. But they are not the truth, right? There's a mistake that people often make, that they assume that because there are numbers, because there's data, this is the truth. And that's simply not the case, right? There's social processes that produce the data we observe. There's error in measurement all the time. There's always error in measurement, right? And then there's artifacts that come into the data collection process because of how the systems are designed and the institutions through which data is collected, right? All of that goes into the data. And just because it's a number doesn't mean it's more objective, right, than someone's narrative of an event, right? Numbers are not inherently more objective than non-numeric data, right, or qualitative data. It's just larger and more uniform. Okay, so all models are wrong, some are useful. Models are toys that represent a real process that we hope to understand, right? That's what we should always keep in our mind when we do statistics. And I'm not saying this to disparage statistics, I'm just saying this to kind of keep us grounded. Obviously, all my research is statistical. I think there are profound things we can learn from it, but we have to be humble, right? We do have to remain humble in how we use them. I think it's very easy to overstate what we learn from models. Very, very easy. And in statistics, we talk about a principle of conservatism. And that means that we always want to err on the side of leaning toward uncertainty. We never want to overstate how certain we are in our results. If we want to make a mistake, we'd rather make a mistake in saying, I'm not sure about this, rather than saying, I am positive about this. We never want to say, I'm 100% positive this is happening, right? Very rarely can we speak with such certainty. What we want to do is kind of be very honest about the limitations of our models, the assumptions of our models, and the uncertainty we have in the results that we've obtained. So stay humble. Okay. So I'm going to review briefly what we did last week, because I know this is kind of big new concepts, right? But ordinary least squares regression or linear regression, right? Ordinary least squares is just the mathematical method we use to derive our estimates for our regression parameters, that is beta, right? We're interested in learning something unknown. So the idea is that if we assume a linear relationship, we say that y, let's try that again. Okay. Y, okay, so we'll say that y is some function of x. We're saying that what happens to y is a function of what happens to some variable x, right? Is a function of x. So some mathematical equation applied to x gives us a value of y. So a regression model assumes that the expected value of y is equal to an intercept plus a slope times x. So for f of x, we're assuming a linear functional form, right? The assumption, the first assumption of our regression model is that the functional relationship between x and y is a line. A linear functional relationship. That's an assumption, right? That's not true for a lot of processes. That's the key assumption of the linear regression. So ordinary least squares is just the mathematical method we're going to use to estimate our, one more thing I want to point out here. We don't know what beta 0 and beta 1 are going in. We know what y and x are. Those are observed data. These unknowns are called parameters. These are called statistical parameters. Anything that we are using a model to estimate that's unknown in statistics is called a parameter. So beta 0 and beta 1 in this case are our parameters. And we're going to use ordinary least squares to obtain an estimate of these parameters. Sorry, one more thing. Technically, beta 0 and beta 1 have theoretically some true value out in the world, right? There's some unobserved true value for the beta 0 and beta 1 that describe the linear relationship between x and y. But we live in this imperfect world where we've only observed a small set of things called our data. So what we're going to actually estimate is not beta 0 and beta 1, but beta 0 hat and beta 1 hat. We're going to estimate those from our model. So these are not the same thing, right? This is one possible realization of the value of beta 0 from all possible realizations that would depend on what we sampled into our data. Right? What data did we observe will determine what our estimates are for beta 0 hat and beta 1 hat. If that doesn't make sense, that's okay, because we're going to talk more about uncertainty and sampling in the coming weeks. But I just want to kind of prime us that beta 0 and beta 1 are parameters. We're never going to know exactly what beta 0 and beta 1 are, right? Unless we have perfect measurement of the full population. We're never going to know with 100% certainty what those are. What we can get is an estimate of the value of beta 0 and beta 1 called beta 0 hat and beta 1 hat because we have limited data. We have limited information. So we can make a guess about the value of beta 0 and beta 1. And the way that we're going to make our best guess is using the ordinary least squares method. Okay, so we minimize the distance between y hat and y. That is, we want to make a line where we say that y hat equals beta 0 plus beta 1x plus epsilon, just to keep it consistent. Right now, I'll say beta 1 hat, beta 0 hat, right? Because we don't really know what beta 0 and beta 1 are. We're just going to get our single estimator, our single result. So y hat is equal to this, where we include our estimates for beta 0 and beta 1 times x and then we have this error term, epsilon, right? The expected value of y is equal to beta 0 hat plus beta 1 hat times x. This is what we expect to see on average. Expectation means average. So on average, we expect to see y to fall exactly on the line beta 0 plus beta 1x. Any individual y, which let's indicate that with an I, any individual y may not fall exactly on the regression line. It may differ from the regression line by some error term sigma. So what we seek to do is we seek to minimize the distance between y hat minus e of y for all y's. For all values of y, we seek to minimize the difference between the observed value and our regression line, right? We talked last time about the residual sum of squares or the sum of squared errors, right? We're seeking to minimize that absolute error. We're seeking to produce the least wrong line, the line that's least incorrect, right? So we say ordinary least squares. That means least squares means the least distance between the squared residuals and the regression line, the minimal distance across all of the data. So this is the line that best fits the data. When you hear best fit, that's what that means. It means it minimizes the possible error, minimizes the error terms. Okay, so to do so, right, we minimize the sum of squared residuals. Here's a mathy way to think about it. The sum of squared residuals is the sum of the squared residuals, like it sounds like, right? So we sum up all the sigmas for the entire data, square those, sum the squares. We want to obtain the minimum value of this for values of beta 0 and beta 1. So we could consider all possible values of beta 0 and beta 1 and seek out those values of beta 0 and beta 1 that yield the smallest value for the SSR, the sum of squared residuals. Now that's technically what the math is doing, but we don't need to do the math, right? Because we have computers who can do the math for us. But that's what the computer theoretically is doing. Really, it's doing it with matrix algebra, but it gives the same result. Okay, so here is some x and some y. And R, we use the LM function to estimate a linear model. In this case, I've defined a vector x and a vector y. And I've said that y is a function, a linear function of x, right? So by default, R is going to estimate a model y I equals beta 0 plus beta 1 xi plus epsilon, right? That's what it's going to do. It's going to give us beta 0 hat is equal to negative 0.5. Beta 1 hat is equal to 1.9. So in this case, we could predict if x were equal to 2, we would predict that y, the mean value of y, the expected value of y, of course, it's not going to be the exact value of y, but what we expect y to be will be minus 0.5 plus 2 times 1.9. So 3.3. Right, we expect y when x is 2 to be 3.3. Now, of course, y when x is 2 is 5. We have an error there of about 1.7. Here's what that model looks like. And there's our regression line. So again, when x was 2, y is 5. Our line does kind of split the difference between all the points relatively well, right? But we still don't have any observation where the point falls exactly on the regression line. The job of the regression line is to give us the best estimate of each point possible, right? The best estimate of each point possible while simultaneously accounting for the full data, right? That's a tricky job, and it usually means we're going to be wrong, sometimes by quite a lot, sometimes by not very much. But the benefit is we get to describe an entire set, an entire system, rather than a single point, right? And we also get to make predictions about things we didn't observe. So we get a lot of benefit off this. So let's kind of go back to how we ask questions with regression theoretically. We might ask, as you did in your homework, right? Are secondary school completion rates for women associated with lower levels of acceptance of intimate partner violence? Holding in our head a theoretical model that suggests that as schooling increases, we expect toleration for domestic violence to decrease because women's relative power in society is increased by access to education, right? So we kind of take a simple version of a feminist theory of social power and apply that to this question to imagine a linear model. We imagine that there's a positive relationship between schooling and women's power that will be reflected in toleration for intimate partner violence, right? And so once we have that linear model in our head, we can think about a regression. The outcome variable here, the Y variable or the left-hand side will be intimate partner violence. That's the thing we seek to model. We are modeling intimate partner violence, our acceptance of intimate partner violence, toleration for intimate partner violence among women. That's what we're seeking to design a mathematical system to explain. That's our outcome. We're modeling it. So when I say build me a model of blank variable, we mean that's your Y, that's your outcome, or you might see people describe that as your independent variable. I don't like to use that language because, I'm sorry, your dependent variable. See, that's why I don't, because it doesn't actually make sense in the context when you're not working in an experimental setting. It doesn't really make sense to call it dependent and independent. But outcome Y. So the expected value of the acceptance of intimate partner violence is some intercept plus some slope times secondary school completion. We're saying this, our abstracted reality is that this works as a line where a country's value for acceptance of intimate partner violence is a linear function of secondary school completion for women, right? That's what we're saying. That's how we're saying the system works. Do we actually believe that's how the system works? Do we actually believe that that's what generates public attitudes among women about intimate partner violence? Absolutely not. Absolutely not. It's far more complicated than that, right? But maybe we can learn something, right? That's the goal here. It's a simplification. This model is wrong, but it still may be useful, right? We still might be able to learn something about the process in so doing it, but this is not an accurate representation of reality. Okay. So our implied prediction about the slope, which we might call a hypothesis. What's the hypothesis here? Using a feminist framework. The hypothesis here is that we should see a positive association between secondary schooling and rejection of intimate partner violence. That is, we should see as secondary schooling increases, women should have less toleration for intimate partner violence. So depending on how we set it up, it's either a positive or a negative relationship, right? But we could say that it's going to be clear that as education increases, we should expect to see lower levels of acceptance for intimate partner violence according to our theoretical framework. Our theoretical framework gives us a prediction or a hypothesis. How we come to the question, how we think the real system works, informs what we think is going to happen, and we should make that explicit when we write. As we write these things, we're not just simply going to the data to discover what's happening. We know something about the world, right? And we want to use what we know about the world to inform what we expect to see in the data. Okay, so in this case, thinking about our regression line, y hat equals beta 0 hat plus beta 1 x plus epsilon. And for those of you who came in late, the hats, you can kind of ignore it. They just indicate that that's an estimated value of beta 0, not the true value of beta 0 that may exist somewhere out in the universe that we didn't observe. But what then, in this context, is the meaning of the intercept? What does the intercept mean in the context of our line? It means when x is equal to 0, in this case, when secondary schooling is equal to 0, our model says on average, we expect a country to have about 40.2% of women tolerate this form of intimate partner violence. That's what the model says. Because obviously, when x is 0, this term cancels, and the expected value of y is just beta 0, right? So we can always think of the intercept as being the expected value of y when everything but the intercept is set equal to 0, right? So when all of our predictors take on a value of 0. Sometimes that's not real in the data. Sometimes there's no, I don't believe there's any country in these data where secondary schooling is equal to 0, right? So it's actually not a real case. The regression model is predicting what we would call out of sample to do this. And so sometimes when we're working out of sample, we should have less confidence that that value is true, right? Because we don't actually have any observations over there to know if that's to test it against, right? But out of sample prediction is something we'll talk about as we go forward. Okay, what does the slope coefficient indicate? Someone tell me what the slope means.
So for every, on average, for every one increase in secondary school, exception for that, partner violence decreases by 0.47.
That's right. And honestly, when you're interpreting these, just round it to like the big, you do 1 or 2 decimal points is all we should ever really use. So 4.7 is fine. I might say yes. So as secondary schooling, if secondary schooling for every point increase, for every 1% of the female population in a country that has access to secondary school, we expect toleration for intimate partner violence to decrease by about 0.5 point. And when I say things like about 0.5 point, I actually want you to write like that. I don't want you to like go write negative 4.753 because we don't actually have that much certainty in our results, right? There's error in our measurement. There's possible misspecification in our model. I would say by about 0.5 point, right? Negative 0.47 is about 0.5 point. I think that's like, be generous, be round a lot in your statistics. Now, not in your computation, but in your interpretation, right? Do not over-report decimals. Don't go out to like 5 decimal points. Our models are not that certain. Our measurement is not that certain. I like to round usually to 1 or 2 decimals, depending on the context. Okay, here's the visual of our model, right? So we have our intimate partner violence measure on the y-axis. That's our outcome. And we always want to plot that on the y-axis. We have our focal predictor, secondary schooling. In this case, we only have 1 predictor. Sometimes we'll have more than one, and we're going to focus our plot on 1 predictor. But our focal predictor here is secondary school, right? And we can see that the hypothesized linear relationship does appear to be present in the data. We do see a negative association between y and x. For higher values of y, we tend to see lower values of x. For lower values of y, we tend to see higher values of x, right? The cloud kind of shifts down as it goes from left to right on the plot. And we've also displayed our best fit regression line, right? So this is that regression line we just estimated, intercept 40.2, 40.2, slope about negative 0.5. So we can see that as we go up by 20, it should decrease by about 10. And that's exactly what we see. Right? We have a slope of about negative 0.5. So for every 1 unit increase, we get a half decrease. So for a 20-point increase in x, we should see a 10-point decrease in y. And that's what we see here. For a 40-point decrease in x, we're going to get about a 20-point decrease in y. And that's what we see there. Now, again, this line represents if I had no prior knowledge about the location of the intimate partner violence acceptance in a country where secondary schooling was equal to 50. I don't know, but someone wants me to ask, okay, so like I have this country you didn't collect data on, but I know that half of the women there went to secondary school. What's your best guess for toleration for intimate partner violence in that country? What would you say? Well, we would go out to 50, find our spot on the regression line. Our expected value is like, I don't know, 18, 17, something like that. We could actually compute it directly using the regression equation. Okay? But our best guess for some country we did not observe will fall exactly on the regression line. Now, as we're reporting this, of course, we'll report that with uncertainty as we go, but we're not there yet. That's an additional thing that we get out of this model that we're not using yet, but we will start to use. My best guess is that it falls here, and I'm this certain about it, right? We're not getting it to the end. I'm this certain about it yet, but we'll get there. Everyone kind of clear on how the regression line gives us the expected value of y? Okay, doesn't give us the actual value of y, gives us the expected value of y. To retrieve an actual value of y, we need to add epsilon to it. And why can't, for this country I didn't observe with secondary schooling of 50, obtain yi? Why can't I obtain the true value of y for a country I didn't observe from the regression line? Because I don't know epsilon, right? I mean, in mathematical terms, it's because I don't know the error, right? You're right, because it's not 100% accurate, but in terms of our model, the reason I can't produce yi is because I don't observe the error term for it, right? If I have the error term for it, I can recover the observed value of y. If I don't have the error term, I can't. Okay, so those are our expected values of y for each observed y, right? This is E of y. This is observed y. And these dotted lines are our errors. So the magnitude of this line, that is how long the line is. The distance between this point and this point is our error term. Y observed minus y expected. Cool? Questions? Okay. So again, I assume that you kind of thought about this as you worked through the homework in terms of interpretation. But you know what I like to do for interpretation, this is something we're going to pick up on today, is to talk about the meaning of the parameters in terms of the outcome and in terms of the predictor. So rather than just saying like beta 0 is 40.2, beta 1 is negative 4.8, right? Rather than saying that, I want to interpret it in terms of secondary education and toleration for domestic violence, because that's what we're interested in, right? So I want to say when a country has no secondary schooling, my model says this is going to be the proportion of the population that tolerates domestic violence. And then I want to think about, okay, what's an interesting scenario? What's like a meaningful difference in secondary schooling between countries? So if one country has no secondary schooling, what would be, like comparing it to a country with 1% secondary schooling versus 0% secondary schooling, that's not especially meaningful, right? Like when we think about differences across countries, 1% and 0%, is that a big difference? I would say no, right? But 0% and 20%, that's a big difference. Maybe we would even want to go so far as between 0% and 50%. Sometimes we can use the standard deviation of the data itself to tell us what is a meaningful difference, right? In this case, let's see what the standard deviation of the data is. There's missings. The standard deviation of the data is 15.6. So my 20 is not far off from that, right? So that means on average, countries are 15.6 points away from each other. And we can think of a one standard deviation increase as being a pretty good jump, as being a pretty good difference between one country and another country. But in this case, I'm just going to arbitrarily pick 20 to say, okay, so my hypothesis is that more secondary schooling means less toleration for intimate partner violence. So I want to illustrate what my model says about a country that has substantially higher secondary schooling than another country, right? And my model says that there's about a 10-point decrease in toleration for intimate partner violence when schooling increases by 20 points. So when schooling goes up, toleration for intimate partner goes down. Toleration for intimate partner violence goes down, and it goes down pretty dramatically, right? 10 points when the maximum is 40, right? The highest value we expect to see is 40 when secondary schooling is 0. A 10-point decrease is 25% of the range of the possible data because it can only go between 40 and 0, right? So I would interpret that as a relatively large relationship. Right? If we're thinking about interpreting this as like positive or negative, big or small, I would call this negative and large. I'm not going to call it an effect. Why am I not going to call it an effect? I can't hear. Right, we have not designed to estimate a causal relationship. This is non-experimental, right? Causality assumes a temporal relationship between a manipulation of one variable and a change in another variable. We don't know here if secondary schooling is what caused this, but we do know that in countries with higher levels of secondary schooling, we see lower levels of toleration, right? And so we're going to be really cautious in our language to not call it an effect, to call it an association, and to say that when a country has higher levels of secondary schooling, we expect to see lower levels of toleration for intimate partner violence. I'm not 100% sure why that is, right? But I know that that association is there. What I'm not going to say is if a country increases its secondary schooling by 20 points, it should see a decrease in toleration for intimate partner violence of 20 points. I'm not going to say that. That's a causal interpretation. And that's something people like to say in a regression context, but that's really a strictly causal inference, because we're saying if I were to manipulate my X variable, it will affect a decrease in the Y variable. But I don't actually know that from this analysis. It could be some other process that is associated with secondary schooling that could be driving an outcome in our variable. Realistically, if we're kind of thinking more philosophically about it, what's probably happening is that secondary schooling is one indicator of women's social power among many possible indicators of women's social power. And so changing one of those variables probably also changes 100 other variables simultaneously, right? And the reason that secondary schooling may change is probably because 100 other variables change that push to an increase in secondary schooling. What this means is these systems are exceptionally complex, right? They're incredibly complex. And so we want to be really careful in thinking about those kinds of causal interpretations. More broadly, we might want to think about whether social systems are particularly good for the kinds of causal inference models that we use in the natural or biological sciences. That's a much larger question in terms of like, with such a complex system, can you actually isolate anything, right, in an experimental context? I don't know that you can, but that's kind of like a much more philosophical question than a mathematical question. Anyway, everyone kind of clear on the correlation versus causation. So when people say correlation is not causation, this is what they mean, right? Just because we observe an association between two variables does not mean there's a causal relationship, and be very cautious in your interpretations to avoid making causal inferences when you don't design for causal interpretation. If you've designed for it, like in our difference in differences model of minimum wage, you can make that causal interpretation conditional on the assumptions of the model, right? Conditional on the parallel trends assumption. If you buy that assumption, then you can interpret this as a causal estimate, right? It's always trade-offs, trade-offs everywhere. Okay, so let's get to new content. That was all review. Linear regression with multiple predictors. So we can extend our basic linear regression model, y equals beta 0 plus beta 1, x plus epsilon, to any arbitrary number of predictors. There's no reason that we can only have one x. We can make this multi-dimensional. So we can say that the expected value of y is equal to beta 0 plus beta 1 x1 plus beta 2 x2. We can just add a parameter and an observed variable to the model. We can add an extra beta, right? Additional parameter into the model. That is, we don't know beta, but we're going to estimate it based on our observed data for y and x, and based on the ordinary least squares method, right? So we can do this for an arbitrarily large number of predictors. If I have 100 predictors and enough observations to support it, then I can have 100 betas in my model. There's no problem with that in principle. In practice, generally, that's not a good idea. But in principle, we can do it. We'll talk about why it's not a good idea another time. But we might write this more compactly using matrix notation. Remember that a capital Y indicates our vector of observed Ys. A capital X, in this case, can represent either a vector of a single X or a matrix of observed X's. So let's kind of think about that for a second. If we're in the IPV data again, and let's say we want to include a model that predicts the burn food outcome with secondary school and no media. In that case, we could have a matrix of X that looks like this. Sorry. I'm not typing well today. Okay. Right. Going between tidyverse and base means you forget to use quotation marks sometimes. Come on. Okay, we'll do it. We'll do it my way. Okay. So turns out your instructor also commits errors in his code all the time. It's part of what happens. But now we have a matrix, right? We have a 2-column and 150 some row matrix that we can call X, right? So location 1, 2 is 1.5, right? Location 3, 1 is 67.6. But this is our X matrix if these are our two predictors in our model, right? So we can describe our vector of Y as just being our outcome variable, and our matrix X as being the collection of predictor variables we're using in the model. So it'll have n columns where n is the number of betas we're estimating as linear as slope predictors, right? So beta 1, beta 2, beta 0, we get for free. But beta 1, beta 2. So in this case, for this model, we know that our X matrix will have 2 columns, and it will have n rows where n is the number of observations of the data. Okay. So our first model was that IPV attitudes is equal to beta 0 plus beta 1 secondary school plus epsilon, right? And that's the actual attitude for a country, not the expected value, because we have the epsilon term in there. If I remove the epsilon term, what do I need to put on the left? What's that? The E, the expected value. So if I remove epsilon, what I have here is not IPV attitudes I have the expected value of IPV attitudes, right? If I leave epsilon in, then I can actually recover the observed value. Okay, so let's add a predictor for region. What we're going to do here is try and think about clustering across places. So when we looked at the data originally, and then theoretically we could think about it too, we could think that different parts of the world are likely to have different underlying attitudes about intimate partner violence as a function of history and culture in that place, right? That the history and culture of Latin America is different than the history and culture of Central Asia, and we might expect that those underlying differences would result in differences in toleration for intimate partner violence. It's a crude hypothesis, right? But like, there's probably correlations across countries that are in the same places, right? Neighbors tend to be like neighbors more generally. Even if we don't want to use like a cultural explanation, we can think of it in terms of networks. We can think about countries that are close to each other tend to be similar because those populations interact with each other. So we might think that proximity to neighbors leads to what we might call spatial clustering, right? Spatial clustering is when units that are proximate to each other geographically have similar values. Spatial correlation. So we're going to add a really simple adjustment for spatial correlation, and that is a region predictor in the model. Now remember, region in our data looks like this. We have a pretty small number of regions here, but we can probably get some value from it. We only have 4 regions. Okay, now in the ideal world, we might like a lot more than that. But if we were to go to our other geographic predictor here, I think we'll find that it's too granular, right? We have 65 countries, 4 regions. Putting a country level predictor in, we'll talk about why that would be complicated later. But for some countries, we only have 1 observation. So we're actually not going to be able to estimate a country level predictor very well. The whistles? Yes. What can you do? Life by the construction site. I mean, they're making progress.
Yeah.
It's kind of remarkable day by day or week by week how much has changed, but yeah. Okay, so here's how we estimate that in R. It's very simple. Our first model stops here. It's A equals IPV. We just add plus region. All we do is for our formula, our y is here. Our tilde says y is a function of this variable plus this variable. And what we know R is going to do is it's going to estimate a beta 0 for free and a beta 1 for secondary school, a beta 2 for region. That's what it's going to do. All you need to do is add a plus in the other variable you want to add. We could obviously do this plus no media. Add a third predictor if we wanted to. Now, what we're going to get here looks a little funky. We're going to get our intercept. What happened to our intercept? Before it was 40, now it's 28. Our intercept estimate changed quite a lot. Our secondary school estimate was negative 0.5. Now it's negative 0.3. The slope has also decreased. You're going to see that a lot of the time as you add predictors, that your focal slope, so we're still interested in the secondary school as our kind of overall relationship of interest. But we're adding what's called a control variable here, right? Control is a weird term for it. Again, that's the kind of experimental context, but we call it a control. We could call it an additional predictor as well. We're saying after we adjust for region, what's the linear relationship we observe between secondary school and our outcome attitudes about inter-partner violence, right? So what do we see here? We've actually gone from 1 intercept to 4 intercepts. That's what we've implicitly done in this model. Because this is a categorical indicator, region. It's not linear, right? It doesn't go from like 0 to 100. So we don't actually get a slope term on categorical variables. We get additional intercepts. And now we can imagine the intercept. So first, note, we have Latin America, Middle East and Central Asia, Sub-Saharan Africa. Is that all of our regions? Because that's 3 region categories and we have 4 of the original data, right? So what's going on? In the original data, we have Middle East and Central Asia, Asia, Sub-Saharan Africa, Latin America. What's missing here is Asia. For math reasons, which I won't go into, we can't have a predictor for every single region. We can have k minus 1. If k is the number of categories, we will have k minus 1 predictors. In this case, Asia is left out. But what that means is that Asia is implicitly the intercept term. When these are set to 0, implicitly it means the region is Asia. So now our interpretation of the intercept term is when the region is Asia and secondary schooling is 0, we expect toleration for intimate partner violence to be about 28. Asia is the reference category. We call this the reference category. It does not actually matter mathematically which category is the reference. Mathematically, if it were Sub-Saharan Africa, we would obtain different estimates, but our interpretations in terms of predictions would be identical. We would get the same results out for expected values of y. We'd get the same regression line, we would just get different coefficients, which doesn't really matter. Okay, so We always leave one category out. But effectively, what we have is, now how would I obtain the expected value of toleration for intimate partner violence when secondary schooling is 0 in Latin America? What I would do is I would add beta 0 to this. So I get 28 minus 11, 17. So my expected value for toleration for intimate partner violence in Latin America when secondary schooling is 0 is 18. So do you see how these kind of effectively work as intercepts? They give each region a different starting point on the y-axis. It'll be easier to see visually. What we've done here, I've assigned color. So I've done the same ggplot, but I've just added an aesthetic for region, and I've assigned color to the region. So I have a geom line and a geom point here. And what we can see that we've done is now each region has a different y-intercept. The slopes are identical, right? Secondary schooling is the same. The the association. See, my training was to think of it like effect, and I'm still trying to undo that, right? Because it's wrong. But the association between secondary schooling and our outcome is -0.3, and that doesn't depend on region. Our model says that's not a function of region. We get the same association everywhere, but we get different starting locations. They have different average levels. Effectively, we're saying that each region has a different average level of tolerance for intimate partner violence, and we're going to let the intercept term in our model account for that. These lines are parallel. They differ from each other by their difference in the sum of the intercept and their estimate. Right? So the effective intercept for Latin America is 28 minus 11, 17, right? So let's look at where it falls. Latin America, right there, 17, right? Asia, right? We said Asia was just the intercept. Our intercept is 28. 28. Said Middle East and Central Asia will be the intercept plus 13.7. So 28 plus 14, 32, 42, 42, right? And then the same for Sub-Saharan Africa, 28 plus 16, 44, 44. Right? What this adding in categorical predictors into our regression model effectively gives us different intercepts for each level of the categorical variable. This can be really useful if we have clustering in our data. This can be incredibly useful if we have what we think of, if we expect that each region has just some different baseline level, right? Or each school or each neighborhood or whatever clustering we have in our data. If we think that there's, or like average heights for cisgender boys and girls, right? We might, or men and women, we might think that like hormones lead to different levels of average height or something, right? Whatever biological process we think is going on. So we want to adjust for particular biological indicators where there's going to be clustering across, cisgender men and women in terms of average height, right? So we're going to see maybe like a 3-inch difference in average height. We want that to be in our model because we think just on average, this group is going to be taller than this group, right? Okay. So that's adding in a single categorical predictor gives us different intercepts for each level of the categorical predictor. So we went from a model with 1 intercept and 1 slope to a model with 4 intercepts and 1 slope. Yeah? What if we want to get crazy and have a model with 4 intercepts and 4 slopes? We can do that. Let's do it. That's an interaction. An interaction is when we include a multiplicative relationship in our data. An interaction is when we allow for a parameter to describe the relationship between 2 variables x, where it's the product of x1 and x2 that is mapped if I made a 3 on 4 line. In the case of a categorical predictor and a continuous predictor, that's actually just going to turn out to be estimating different slopes for each value of the categorical predictor. When we have an interaction of two continuous predictors, we're estimating a multiplicative relationship between the two, right? A dynamic relationship where the relationship between X and Y depends on the locations of X, right? We'll talk about those as well. Those are harder to interpret, so we're going to start with the categorical approach. I think interactions are a thing that we can look at on our data, and it gets really, really difficult to look at. So here's how we model it. We model it with the multiplication sign, the asterisk, this multiplication in R. So we write our equation, we include secondary school and region. This is not strictly necessary. R will do this implicitly if we just include this interaction term. So I'll show you what this does. Easier to show than tell. So here's our coefficients for the model. And before I explain what these coefficients are, you can see that we've got 1, 2, 3, 4, 5, 6, 7, 8 coefficients now. If I remove these terms, I will still get 8 coefficients. By default, if I have an interaction term in the model in R, it will also estimate intercept terms for each value. So, but mathematically, it doesn't matter. So I think for now, I'm going to write it out, secondary school plus region plus the interaction, because that's how we're writing our mathematical equation. But R will do that work for us in the background if we don't write it out. Okay, so because we look at coefficients, I'll briefly explain what these are, but I think visually it's much easier to understand. Our intercept is the reference still Asia? Yes, it is. So our intercept term, 27.8, is our expected value for Asia when secondary schooling is equal to 0, right? Because Asia times 0 is equal to 0, right? So we get our intercept still has the same interpretation. Now, when Asia is equal, when we're in Asia and we have secondary schooling of 20, our expected value is 27.8 plus 20 times negative 0.3, right? Asia equals 1, secondary schooling. Effectively, what we're doing is we're now saying that the slope for each region differs. So in order to obtain the slope for Latin America of secondary school, I would add negative 0.32 and negative 0.14. In order to obtain the slope for Central Asia, I would add negative 0.32 and plus 0.2. In practice, what this means is the slope for Asia is negative 0.32. The slope for Latin America is lower than the slope for Asia by 0.14. The slope for the Middle East and Central Asia is higher than the slope for Asia by 0.2. The slope for Sub-Saharan Africa is lower than the slope for Asia by 0.05. Now, that's all really technical and difficult to understand, right? That stinks. So let's look at it this way. This is easier. What our model does, once we have the interaction term in, is we get, as before, our 4 separate intercepts. 1 for each region, right? But now we also get separate slopes for each region. We allow each region to have a different underlying linear relationship between secondary schooling and tolerance for intimate partner violence. We've kind of relaxed this. This is a pretty strong assumption. Every region is going to have the same relationship. Secondary schooling is going to do the same thing everywhere, right? That's a strong assumption. What if I don't think that's true? What if I think secondary schooling could do different things in different places, right? Then I can relax that strict kind of parallel slope assumption and allow each region to have its own slope. So our model now has a little more flexibility to fit the data. And we can see that the green line now is really focused on being centered around the green points. The red line is really focused on being centered around the red points. The purple line is really focused on being centered around the purple points. The blue line is really focused on being centered around the blue points. In practice, we're actually estimating 4 different regression equations. Like that's functionally what we're doing, but we can do it with one model. So this interaction term allows us to really flexibly fit a model for different levels, different categories of our data, different groups within the data. Now, I don't know if you've heard of a multi-level model before, but this is a very simple approach to the problem of clustering in the data that we will extend to a multi-level model as we get more advanced. Okay? This is the simplest way to estimate a model that accounts for structure in our data. Yeah.
So what would be the benefit of doing it?
This is much simpler.
It's much simpler. Okay.
This is far simpler to interpret, and it's far simpler to estimate.
And it is technically it's still accounting for country, right? Sorry about the
Yeah.
confusion, but it's not really looking at the effects of how it changes.
Well, so we have different assumptions in our models. Remember our models, think of them as like we put a rubber band here to make it do this, right? We kind of like let our model do different things. So in this case, we're letting each country have a different starting value, a different average, a different intersect, but we're not saying that secondary schooling works differently in different countries.
Okay.
We're saying that, in fact, we're saying it doesn't. We're saying it works the same everywhere. Secondary schooling works exactly the same everywhere, but each region starts from a different place, right? They have a different, effectively, y-intercept. So we can imagine this is kind of moving over time where each country, again, this is the causal interpretation, but it's kind of easier to see it on the graph. We're assuming that each region starts at 0 and they have different starting locations. And then as secondary schooling increases, they decrease at a consistent rate across regions, but they're still going to end up in different places because they started at different places. You can think of this as they have the same velocity, right? They're all driving a car along, and that car goes the same speed for each region. So whichever country has the highest value at the end is going to depend on which region had the highest value at the start. If they have constant slope. So this is much simpler model. And we can see that for our 2 predictor model, one way we can think about model complexity is by thinking about how many coefficients we're estimating. So here we're estimating 1, 2, 3, 4, 5. This is a 5-parameter model where we're estimating 5 coefficients. That is the coefficient here. We call it a coefficient because we're like multiplying x1 times beta1. So beta1 is the coefficient for x, right? Meaning coefficient meaning the thing we multiply it by. So the coefficient for secondary school is minus 0.33. This is an estimate of beta1, the parameter beta1, right? So this is a 5-parameter model, whereas our intercept model has 8 parameters, right? So the more parameters we add to the model, the more complexity we're adding to the model. And once we've baked in more complexity, we start to stretch our data. The danger here by going too far with this is a danger called overfitting is the thing we want to avoid. Once we do this, that is stretching the data to a point where it's the model is more complex than the data allows for. Right? We'll talk about that more later. Let's take 5 and we'll come back at 11:06.
This would be a more accurate interpretation of how.
Back to it. Okay. So feel free at any point to stop me and ask questions. This is new material. This is hard stuff. I want to clarify that interactions are super difficult to understand when you're just looking at this, right? When we're just looking at the coefficients, that's really, really difficult to understand. I strongly encourage you, anytime you estimate a model with interactions, to make a visual of it. Because once we get here, I believe that this gets dramatically easier to understand what the model's actually doing, right? We go from, these 9 numbers to a plot where we can see what the underlying relationships actually are. Because once we have an interaction model, to think about what's going on in Latin America, we have to think about, okay, first I have to add this, and then I have to add this to this, and then I can plug things in. It gets messy, especially once our models get more complicated. Maybe we have multiple interactions. Things can get really, really difficult to work with from the coefficients. So I'm a strong believer in always visualizing your model. Okay. So let's work with some new data. We're going to kind of work collaboratively now. This data is built into R. You can access it by going to your console and typing in data MT cars. At this point, I actually do want you to work on your in R. We're going to kind of abandon the slides in a moment. So load in the data with data MT cars. Then we'll look at the head of it. This is just built into R. You don't need to do anything else. What this data is it's data on like 30 cars from the 1970s on a bunch of different characteristics of the car, right? So we have these variables. We have miles per gallon is MPG. Sil is number of cylinders. Disp is engine displacement. That's how much gas the engine pushes through. HP is horsepower. DRAT is rear axle ratio. I don't actually know what that is. Weight is weight in tons, 10,000 pounds. QSEC is its quarter mile time in seconds. VS is the engine, whether it's V-shaped or straight. I don't know what that means either. I'm not much of a car person. AM is whether it's an automatic or manual transmission. Gear is the number of forward gears. Carb is the number of carburetors. Okay, so we have a lot of predictors, a lot of variables, right? We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 variables on 32 cars, I believe, right? So we can go over into R. I'm going to clean this up. We type dem to get the number of dimensions in it, 32 observations with 11 columns, right? 32 rows, 11 columns. Or I could just do in row, MT cars, in call, MT cars to do the same thing. In row, number of rows, in call, number of columns. Okay, so our outcome of interest is going to be miles per gallon. We want to build a model for fuel efficiency. So let's build a model. Our goal here is to say MPG is equal to some function of features of the car X. Don't know what those are. But we're going to say miles per gallon is related to some other features of the car that we're going to call X. And we want to think about what a model should be for that. So based on the variables we have in the data, which you can just do head on the data again if you want to see them, what do we think after that should look like? Let's build a single predictor model first. Right, we're going to assume a linear relationship. So we're going to assume that there's some linear function f of x that determines the relationship between miles per gallon and our single predictor. What predictor do we want to start with of all the ones we have in the data? What do y'all think? Horsepower? Why horsepower? Okay, so horsepower reflects how much gas the engine consumes in order to drive the energy of the vehicle. Yeah.
I don't know it that way, but yeah.
I mean, we're like, I just want to think about it theoretically.
Yeah,
right?
I have no idea, but I know that that's a common thing. I don't know the ins and outs of the car.
Yeah, so no, I think it's a great idea. Horsepower is basically the power of the engine. It's the energy the engine produces. So let's think about MPG is a function of horsepower. And what is the function that we're going to be estimating in our OLS model? We're going to say the expected MPG is equal to what? Our intercept is called beta 0, right? All lines have an intercept and a slope plus beta 1 horsepower. Right? So we're saying that the expected value of fuel efficiency is a simple linear function of horsepower. Estimate that model. Go into R and estimate that model. And remember, to estimate a linear model in R, I don't want to show you how to do it just yet. With this particular data, we do ln, our outcome y, tilde x. So those are the variable names. We do data, the name of our data frame. Right? So we use the ln function, y by x, and then we provided the argument data equals whatever the name of our data frame is. What's that? Yeah, data is going to be empty cars. So take a second to work on that. Raise your hand when you think you got it, and I'll come take a look. What did your error say? Did you load in cars in? Oh, so you just wrote in y by x, but y is not what we're after. Y is a outcome variable. What's our outcome variable in this model? Right, so try that again. Instead of y by x, you write in our outcome variable and our predictor. Substitute y and x for our outcome and our predictor. Yep, great. And you might want to store this in an object, right? ln is going to produce output, so we might want to store it somewhere. Call it like M1 or model 1. Yeah, it's just what it's saying. That's it. Investigated a regression model. Good. Good. Good.
Sorry, I'm about to raise my hair.
No, you're good. You're good. All right, everyone's got it? Oh, yeah, sorry. It's just data equals. So when I say df there, I just mean the data frame is the object that stores our variables and columns and rows. So you don't need data frame around it. That'll work, but you could actually just say data equals empty rows. You don't need that data frame. If you just push up on your keyboard, you don't have to copy and paste. You actually just push. Repeat the last line of code. Okay, perfect. Okay, so what was the model we estimated? What was the estimate for beta 0? EMPG equals 30.1 plus minus what? 0.06.07. Okay. Our expected value for miles per gallon is 30 minus 0.07 horsepower. So if we have, what's the expected value for miles per gallon when horsepower equals 200? What's our expected value? Miles per gallon when horsepower equals 200. To obtain that, 44, 116. So what we want to do is 30 minus 0.07 times 200. Right? So that gives us 116 or yeah.
Just 16.
Just 16. Okay, 16. Okay. Sorry. 16 miles per gallon. So we have a 200 horsepower car according to this model. Okay, cool. That's a reasonable miles per gallon range, right? That's like in the realm of things that I think cars can do. That's good. It's giving us a sensible prediction. That's kind of always a sniff test with your model. Does it provide you with a sensible prediction for a real value? Okay, cool. In this case, it does. Great. Now you did that by hand, right? Which is cool. Let's estimate this again, and let's try a different way to do that. So let's do M1 is equal to LM of MPG by HP data equals MT cars. And then I look at M1, and when I just call the object M1, it's an M1 it's an LM object, which is a special thing in R, and it's going to give us the formula, and it's going to give us the coefficients. This is the easiest way to look at a model, right? Remember before we used coef to just extract the coefficients portion of this object. If I look at what's inside this, it's actually like a whole bunch of stuff. If I do STR, remember like STR on MT cars, it's going to tell us it's a data frame with 32 observations of 11 variables. And it's going to tell us what those all are. MPG is a numeric variable, numeric variable, numeric. It's all numerics. We could have a character variable there or a factor variable there. And then it's going to give us like the first 6 or 7 values of that. But STR on M1 is going to look weird, right? Because it's a different kind of thing. It's a list of 12. So M1 is actually a list object, not a data frame object. Don't worry too much about that. But list objects in R can hold an arbitrary number of things. Lists can just hold whatever. In other programming languages, we might think of these as arrays, right? But a list can just hold anything. We can store anything in a list, and it has dimensions, right? So like M1 bracket 1, rather than using a single bracket to index list, I use a double bracket to index lists. We'll return the coefficients, right? Because we saw up here, the first thing in here in this list was coefficients. If we want to get weirder, I can index, I want object 1 from list M1, and then I want element 1 of that vector, and it'll give me just the intercept. If you ever find yourself needing to work with list objects, which you will when you get more advanced, you'll kind of know what that is when you see it, but don't worry about it for now. Anyway, M1, by default, when I ask for the output of a linear model object, it doesn't give me everything. It just gives me the formula and the coefficients, which is useful because that's all I want to see right now, right? Okay. So this is my model. Now, I'm asking this question. So of course, what I could do is I could say 30.09 minus 0.68, 0.68 times 200 to obtain my expected value, 16.49, right? But I could certainly automate this, right? This is all a program that should understand how to do this stuff implicitly. So let's automate it. What I'm going to do is I'm going to create an object called new data. And into this object, I'm going to make it a data frame that includes the predictors that I want to estimate over. So in this case, I want to say HP equals what? For my prediction data, I want to say it equals 200. That's what I'm interested in predicting. Now I have a new object called new data. Could be called whatever I want, right? Could be called pancake. Really doesn't matter. Use whatever names you want. Okay. Now what we can do with this is we can use a function called predict. Predict will take its first argument will be a model. And in this case, we're going to give it M1, right? And the second argument we want to give it, we want to say new data equals pancake. What it's going to do is it's going to generate regression model predictions for every element of new data. It's going to run it through the model and give us predictions. Right? So this will automatically apply the regression formula to our supplied new variable. Now, if I just do predict M1, it's going to run it over the observed data. So now it's going to run predict over every single row of the original data, and those data are labeled, so it's going to give it to us for each name of the car, right? If we look at head of MT cars, we'll see that this matches. Mazda RX-4 is the first one. We can see that the HP is 110 on that. And so for a 110 horsepower car, it's going to predict 22.6 miles per gallon. For the RX-4 wagon, it's a 110 horsepower car, so it's going to predict exactly the same thing. And this is going to start to show us the limits of the model, right? 110 horsepower, both cars, prediction 22.6, identical. Observed, actually they are identical. I would expect that this would have slightly lower MPG because it has slightly higher weight, right? And maybe it does on, maybe this is rounding that we're seeing differences, but we can see some limits here. But so what we're going to get is we're going to get the prediction from our model, right? 22.6 if we just run predict with no new data argument, right? If we just run predict over the model, it'll give us the expected value for each row of the data. But if we want to predict something new, right, we can make our new data, which I don't know, arbitrary name. I just want to, like, it doesn't matter what you call it whatever you want. It just needs to have the same structure as the original data. And it only needs to have values for those variables that are in the model, but it does need to have values for everything in the model. So we're going to say in this case, right, HP equals, let's say I want to predict 2 MPG values, 100, 200. Now let's predict M1 on arbitrary name as our new data. And let's make sure to clarify to our that this is the new data argument, right? The predict function looks for an argument called new data to predict over. If we don't give it new data, it'll just predict over the observed. And now we get 2 predictions, one for 100 miles per gallon, one for 200 miles per gallon. What if I want to get a whole bunch of predictions? Maybe I want to get every possible value between 50 and 200, every integer between 50 and 200. Now I have arbitrary name is a data frame with 1 column and 151 rows, where each row steps up horsepower by 1. No reason I can't predict on that. Predict M1 on arbitrary name. And I'm going to get 151 predictions, right? That correspond to each value of miles per gallon from 50 to 200. And once I have that, I'm in business, because what I can do with that is I can call this, what is this? This is y hat. This is our expected value for y, right? Which we could call y hat. And x, right, is equal to the values in arbitrary name, miles per gallon, right? So I can use the plot function to say plot arbitrary name string MPG. I'm using the base plot function just because it's a bit easier here. And y hat on the y. Oh, do they? Oh, right, HP. They differ because MPG doesn't exist there. And that's a really ugly plot, but that is my estimated regression line. Represented as a series of points where I've computed the expected value. Yeah.
I was going to ask, I think you did it last class. Model, create a flat model object.
Yeah. I'll show. We'll come to that. I just want to kind of illustrate basics first. So what we've done is we needed two things to compute to display that line as estimated points. We needed y hats. That is our expected values of y. And we needed a range of x's over which it was going to predict. And we can get this, right? This looks unpleasant, but this is the easiest way to visualize your model. The easiest way to visualize your model is to generate expected values over a range of predictors of interest. So that's, we'll kind of keep coming back to this as we go, but this is conceptually what we're doing. We're going to use predict to compute y hat, which we could do just, by hand. No problem with doing it by hand, beta 0 plus beta 1x, right? But we can automate that with R to generate predictions over whatever range we're interested in, right? Here I said arbitrary name is going to be 50 to 200. No reason I couldn't make it 10 to 300. Be whatever I want. Yeah. In the predicts call. Yeah, so I could do predict M1 new data equals data frame MPG or HP equals 50 to 200. That'll work just the same. Yeah, so I don't necessarily need to define my new data as an object, but I can. If I want to define it in line with the predict call, I can definitely do that. Okay, that got a little advanced, but what we've done is we've taken M1 and we've generated predictions from it. Ultimately, that's what we want our regression models to do. We want our regression models to be able to help us learn about what we would expect to see for our outcome variable for different levels of the predictors. What can you do? Okay, so let's kind of flip back for a second. Now, I already kind of gave you a clue as to where I'm thinking, but right now, we said that the expected miles per gallon of a car is equal to function of horsepower, right? Where that function, where f of the speed equals beta 0 plus beta 1, right? Okay, so do we think that actually describes the process that determines the car's miles per gallon? No, right? That's a really simple approach. Now, obviously, we've seen that horsepower is related to miles per gallon, right? Clearly, it's a function of it, but is there more in the system than simply the power of the engine? What other variables do we think might matter? What other variables do we think might be related to the fuel efficiency of a car? Say louder. Weight, right? Weight might be one feature of it. Perhaps the number of cylinders or engine displacement in the car could be related to it as well, right? But let's stick with weight. I think weight's a good one. So now what we're going to say, this is M1. Now let's make M2 B of MPG equals F horsepower and weight. Now we're saying the miles per gallon is a function of horsepower and weight, and we're going to say that this takes the functional form beta 0 plus beta 1 horsepower plus beta 2 weight. Let's make that model. And a hint, if you take your code from model 1 and add a single thing to it, You've estimated model 2. Left-hand side, it's over there. That's our left. Now our right is our predictor. No, not wrong. So what's our functional formula? Plus. So you only ever your formula distinguishes our outcome from our predictors and roots to position on our predictor. Okay. You don't have to take on the equals. That's almost right. Right? The left hand side is MPG, right hand side is HP fluctuate. Okay, everyone feel okay about this? So let's generate. First, just do it by hand. You can use predict if you want, but let's generate what is the expected miles per gallon when HV equals 100, and weight equals 3. How would we solve that? Right? We just do beta 0 plus beta 1 times 100 plus beta 2 times 3. Pretty simple. We can do that by hand, right? And if we're only going to generate one prediction, oftentimes it's easiest just to do it by hand. But let's get fancy. Okay, so let's estimate model 2. It's a linear model of MPG by horsepower plus weight data equals MT cars. I'm actually going to open up a script file because I think I'm going to start writing some code for visualization that'll be easier to write on a script than it will in the console. But so M2 is that. Once I start working in a script, I want to like write all the code I need to support it, so that if I run it from the beginning, it'll execute everything below faithfully. Right? If I were to start a new session of R, I'm going to bring tidyverse into because I want to use ggplot now. Okay, data empty cars M1. It's the same thing as M2, right? But without, so I'm just going to copy and paste that without weights. And when I like hit Command S habitually when I'm writing code. And I think you should get in that habit too of just like always save everything you do after you make any edits on the file. And R will tell you that because it'll have like a little asterisk and a blue symbol when it's unsaved, right? I don't actually want that, but R will remind you to save all the time. Just every time I type anything, I have a habit of just hitting Command S. Okay, so we have M2 and M1. Now from here, what I can do is I can source it. And it'll, when I click the source button, it'll run everything in the script on the console. Okay, and that's, I think, once we get to writing more complex programs, that's a really good habit to get in, is every time you add something new, source it to make sure that it executes completely, to make sure that you don't have any errors in your code. Okay, and then I can go over here to my console and look at my results. M1, M2, looks good, right? Okay, so let's say, let's predict for M1 and M2 over a range of reasonable values for the predictors, right? Okay, so we'll say new data. Actually, first, what I want to do, a good practice to get in is to predict over what you actually see in the data, right? We don't want to predict necessarily for a car that has our maximum in the data is 335 horsepower, right? So our model is fit to data with a car with an engine as much as 335 horsepower. Do we think this model would perform well at predicting a car with 1,000 horsepower engine? It hasn't seen anything with 1,000 horsepower engine, so it has no empirical support for predicting anything at that range, right? There could be some weirdness in what happens once a car gets past the 335 point that takes on a different functional form, and we don't know about that. So typically, we don't want to predict what's called out of sample. Predicting out of sample means predicting for values that you have not observed, right? Predicting for things that are just different from what you've already seen. You can do it, and that's actually the real test of a model, is out of sample prediction, but you want to be very cautious when you do it because it's very easy to be wrong, right? And we want to think carefully if we're designing a model to predict out of sample. For now, we're not going to do it, okay? So what I want to do is let's establish a range for predictors based on the observed data. So I'm going to say my new data is going to be called test data, and it's going to be a data frame. And I have two variables, right? I have, what are my two predictors? HP and weight, right? Okay, so I'm going to say HP is equal to a vector that's going to take on values between the minimum of MT cars HP through, actually, I'm going to introduce a new function here called sequence, SEQ. So what SEQ will do is it'll give us a sequence that starts at one place and ends at another place. It's going to take as its maximum, as its endpoint, the maximum value of MT cars $HP. So let's see what that does first. Right, minimum MT cars HP gives me 52. Maximum MT cars gives me 335. So my sequence, and here's, we can pull up the help file on it. Sequence generation will run from 52 to 335. Now, the difference between sequence and just doing like 52 to 335 is what's going to happen for this sequence 52 to 335 if I write it with a colon. It's going to step by 1. It's going to go from 52 to 335 with an interval of 1, right? And that's useful, but maybe I want to have a different interval, or maybe I want to have a predefined length of my vector. In this case, I want to have a predefined length. And you'll see that there's an argument we can use in sequence called length.out. I'll explain why we want this in a moment. I want to make a length.out of 50. What that's going to do is it's going to create a vector that's 50 long that goes between the minimum and the maximum with equal steps. And it'll decide what that step needs to be, right? In this case, that step is going to be like 5.8, right? But it's going to take that, it's effectively going to go, okay, the maximum was 335. It's going to go 335 minus 52 divided by 50. Right, that's going to be the step length, because it's going to, it tells, I'm telling R, I want you to make a vector that goes between these two values with equal steps that's 50 long. So they're going to be 5.66 apart. Okay. So now my test data frame has one column with a vector called HP that goes from 52 to 50. I'm sorry, 52 to 335. And it's 50 rows long, because we told it length.out equals 50. Now, why did I do that? The reason, I would really like this indented differently. The reason I did it that way is because I want to make another variable. Oh, you know why? That's why. I want to make another variable in there. We have weight in here too, right? Weight is our other predictor. And what do we know about data frames? We know that data frames, can we have a data frame in one variable that has 50 rows and another variable has 200 rows? They have to be rectangles, right? Each variable must contain the exact same number of rows as every other variable in a data frame. We cannot have any shape for a data frame other than a rectangle, right? So we have to have a consistent number of rows for every column. That's a feature of data frames. So if I were to do HP runs from 52 to 350 by multiples of 1, how many would I get, right? Let's say length 52 to 350. That's going to give me 299 observations. Now, what's the minimum value for weights? Let's see. Empty cars, weights, it's 1.5. And the maximum is 5.4. So if I were to then go and do the same thing for weight that I did for cars by going step by 1, right? These are really different units of measurement. So if I step from like 1 to 6, I only get 6 values, right? That's not 50. I cannot put those two things in the same data frame. I can't have a data frame that has 350 weight values and only 350 horsepower values and only 6 weight values. I have to have an equal number of rows. So that length.out argument in sequence is going to force the data frame to stay a rectangle. And that's really useful. Okay, so sequence, min, empty cars, $, weights, max, empty cars, $, weight. I don't have to use the minimum and maximum. I'm just doing that because I want to predict along the whole range. I could start from like the first quartile to the third quartile, or I could start from like the 5th percentile to the 95th percentile. You can choose whatever range you want, right? This is arbitrary. It's our predictions. We can do what we want with it. But I think it's sensible to use the observed data and the minima and maxima to do that. Okay, so we've defined our new data frame. And because I've set them both to have a 50 length out sequence, let's see what happens, right? I get a 50 by 2 data frame. And we'll notice that we get a different step size though, right? For horsepower, we get like a 5.77 step size. For weight, we get like a 0.08 step size, right? The difference between 2 and 1 here is 5.77. The difference between 2 and 1 here is about 0.08, right? So the step size is different because the scale of weight and horsepower is very different. This is measured in thousands of pounds. This is measured in horsepower, which I don't actually know what that is, right? But who does? It's a weird imperial measure, right? We could measure it in like newtons or something, but yeah, whatever. Okay. This is a little tricky, but this is a algorithm for generating predictions that I think you will find very useful. And I use all the time. I use this procedure all the time in my research because it makes interpretation really simple. Because what we can do now is we can say y hat m1. We can generate a vector of predictions over this hypothetical data we've created. We don't actually observe any car with a 1.592816 weight, right? But we can imagine a car with that weight, and we might want to predict along it so we can get a continuous line that we can look at. So for M1, how would I generate predictions for this? I would predict with M1, comma, new data equals what? Test data. Test data is the name of the data frame that I've put my, we could call it counterfactual data, prediction data. It's fake data, right? I often call it fake data, right? Because it's not it's not real data. It's just some hypothetical range that I'm working over. We'll call it new data equals test data. And then we're going to get a vector of y hats. Those are our predictions from model 1. Now let's do the same thing for model 2. Y hat M2, predict M2, new data equals test data. And let's see what we get there. So compare. Model 1 predicted row 1 at 26.55 miles per gallon. Model 2 predicted so we predicted like row 1 in new data. So let's actually like pull that out. Okay, so test data bracket 1. So we'll pull out the first row. So for an engine with a car with 52 horsepower and 1.51 weight, what do we see going on? Well, for y hat M1, we predict the miles per gallon on that car for model 1. Engine 52 horsepower, 1.5 times 1,000 pounds weight. It's going to have a 26.5 miles per gallon. Y hat for model 2, it's going to predict 29.7. We get very different predictions from those two models, right? Because we have incorporated an additional predictor in. We get a different fit. But what we can do now is we can prepare this for plotting. So what I'd like to do is I would like to create something new called plot data. That's going to start from test data. What we're going to do is we're going to mutate. So we're going to take test data as our starting point, right? Because that includes our predictors. We know we want to plot those. It's going to mutate where y hat 1 equals predict M1 new data equals test data. Now there's no reason I couldn't just put my y hat M1 object in there because I've already done this, but we can comment this out. Let's not run this code. I'm going to run my predict function within my mutate call. Let's call y hat 2. Not N1, M1. M2, new data equals test data. Let's see what we get now. That is super convenient for plotting, right? Now I have my X's and my Y's that I might be interested in plotting all in the same place, right? I have a single data frame that includes my values of the predictor and my expected values for the outcome. That's really useful. So what we can do from here is a really simple ggplot, where we take as our data, plot data, our aesthetics. Let's start with plotting out the horsepower predictor because that is active in both models. So we'll say X equals HP. What's Y going to be equal to? Start with Y hat 1. And then let's draw a geom line. Okay. I'll show you what both geoms do. Let's start with the geom point, just to show you what it does, and then we'll move on. The geom line is actually what we want. That's our geom point for it, where it gives us a scatter plot with each point. What we really want to see is a line. Yeah. Okay, so that's our first estimated. That's model 1. That's the estimated relationship between horsepower and MPG for model 1. That's the expected value. Now, let's add the second one in. I can specify a new aesthetic inside a geom. What aesthetic do I want to switch out to show model 2? Y, right? I want Y to now be equal to Y hat 2. I have 2 possible values of Y in this data frame, right? So I'm going to switch out my Y to be equal to Y hat 2. And to allow us to distinguish between these 2 models, I'm going to change the shape of the type of this line from solid to dashed. And I can do that with LTY, which stands for line type, equals 2. So those are our 2 regression models, right? This is model 1. This is model 2. And I'll post this code on the Slack when we're done, so you can have this as a sample. Okay, so we visualized our 2 regression lines as a function of horsepower. Is weight displayed on here anywhere? Nope, it's not on here at all, right? So what if we want to visualize the relationship with weight? We've actually not really set up our, we'll do it. Okay, so we don't have, yeah, we'll do it. Okay, so we could, let me see if this works. X equals weights, Y equals Y hat 1. Actually, yeah. Yeah, so what we've done here is we've actually inadvertently made weights and horsepower move together, right? Let me show you what this would look like in a different context. So before we get to a 2 variable setup, we've systematically varied miles. We've systematically varied horsepower from 52 to 350, and then predicted over all of those values for miles per gallon across our 2 models here, right? So everyone's kind of clear on what we're looking at. This is the expected miles per gallon for model 1 and model 2. Now, let's set up to predict for weight. So what we want to do now is we want to ask how, obviously model 1, what's the prediction for weight going to look like in model 1 if we hold horsepower constant? It's going to look like a straight line, right? If horsepower equals 150, weight is, that stands for belongs to, is in the set, I don't know, 1 to 6, right? It doesn't matter what value of weight takes on because horsepower is constant for model 1, right? Model 1 does not consider weight. So if horsepower stays the same, it doesn't care. It's going to predict the same value of miles per gallon for every possible value of weight. So we're just going to get a flat line there. We could work through that, but it's not that interesting. So here, actually, this will work just fine. We can actually, okay, so because we know that model 1 doesn't predict as a function of weight, so we'll exclude it. So we'll only look at model 2. We'll switch out x equals weights. And we get this line. That's our regression line for weights based on model 2. But the assumption here is that we're holding horsepower constant, right? So we say as weight increases from 1 to 6, the problem with this prediction, though, is we've also allowed weight to vary, right? So let's actually kind of switch this up. And let's say, instead of allowing weight to vary, making it a sequence, let's make weight equal to a constant value. And let's make it equal to the mean of the data, right? When we want to hold something fixed, it's usually a good idea to take like a mean or a median as our starting value, because that's, you know, at the center of the distribution. Most cars look something like this, so that's a good place to start. So we're just going to set it equal to MT cars $weights. And if I have a data frame that has a length of one vector, and then I give it a constant for another, notice I haven't said like mean weight is just length 1, right? But it's going to repeat automatically for the length of the data frame to fill it out. So it's just going to be a constant, right? For every value of horsepower, now we have a weight of 3.217. And this is actually going to change our first plot too, because we were systematically varying weight. Now this is going to look quite different, right? Now what this model is saying is if we hold weight constant at 3.2, right, this is our expected line for model 1. This is our expected line for model 2. What do we think this is telling us? That horsepower might actually be less influential than we thought, right? Because once we've adjusted for weight, for 2 cars at the same weight, we don't actually expect to see as big a difference in fuel efficiency as we did in this car. Right? The difference between a 50 horsepower car, a 350 horsepower car, assuming weight is held constant at 3.2, Model 2, the difference between like 23 and 17, as opposed to a difference between 27 and 4, right? Huge difference. Let's think about that for just a second before we move on to more visuals. M1, M2, right? These are our 2 models. I want to pull out a new statistic that we haven't talked about before called R squared. I can use the summary function on M1 to give me a much more verbose presentation of everything in that M1 object. This is telling me way more than just this, right? When I do summary, it's going to give me this presentation. Now, there's a lot going on here. We have our formula. We have the distribution of the residuals. The residuals, again, are the errors. So the largest error on the negative side of the data is minus 5.7. The largest error on the positive side is 8. That doesn't really tell us much right now. We can kind of ignore this. Here's our coefficients, right? In that first column are these 2 values, the estimate. So that's what we're looking at for now. But I want us to look at this R squared value, 0.6024. R squared is a simple number that tells us what proportion of the variation in our outcome variable is explainable based on variation in our predictor variable. So we can interpret this as saying about 60% of the variation in miles per gallon, if we assume a linear model, is explained by horsepower. This is a crude measure of model fit. People stretch this R squared number way too far often, but it's a useful, immediate, quick check on how well my model fits the data, right? So this is telling us that about 60% of the variation in miles per gallon is explained as a linear function of horsepower. Now let's look what happens when we look at model 2. What's R squared now? would we say we've improved the model fit? Quite dramatically. We went from 60% of the variation in miles per gallon explained to 83% of the variation in miles per gallon explained. It's clear that weight also plays an important role in the distribution of fuel efficiency, right? We've added information into our model, and because we've added this information, we get a better explanation of why. Our model fits the data better. We have improved our model fit. So if someone asks you to compare model fits, the easiest way to do that is to look at R squared. Has R squared increased? The problem with R squared is R squared automatically increases when we add more data into the model, even if it doesn't actually relate to the predictor because of the way it's computed. So like I can add random noise into my model and R squared will go up, right? So be careful with R squared, but it's really useful here. And it can tell us in a very crude way, you know, oftentimes people will like look at these significant stars and be like, okay, well, that's got stars, so it must be important. This is a better way to look at it. Did this go up? Is this a better fit? And in this case, yes, the weight model is a much better fit, which means it's going to generate better predictions, right? When the model has a higher R squared, it is likely to generate more accurate predictions. We can also look at that in terms of the range of the residuals, right? Here on this model too, our errors range from minus 3.9 to 5.8, right? So the range on our residuals is compressed compared to model 1. On model 1, we had a much larger range, minus 5.7 to 8.2, meaning our residuals were wrong, our guesses were wrong by more in the first model than in the second model. Okay. So that's R squared. Okay, let's do this with one more data set and then we'll call it for the day. Yeah.
So for so that's showing the R squared values of the added kind of influence of horsepower and weight together, right?
Yeah, this is effectively the, so this is model 2, this is model 1. We improve our model fit. We improve our explanatory power on the outcome by about 20%.
Most of that is coming from weight now, not.
Yeah, it's coming from the joint function of weight and horsepower. Right, well, let's look at this. We could also just ask weight alone, right?
Weight alone is going to explain.
That's going to be different. Let's call that M3, LM, MPG by weights to see if we can sniff out, okay, is it really just weight that's doing all that work? Or is miles per gallon adding something? And here we have a 0.75, right? So the difference between the model with both predictors and the model with weight only is actually kind of small, right? With weight only, we get an R squared of 0.75. With weight plus miles per gallon, we get an R squared of 0.8, right? So the improvement in fit by adding in horsepower after we know weight is not that dramatic. So what we can interpret that as saying is that horsepower, once we already know weight, knowing a vehicle's horsepower doesn't dramatically improve our understanding of how fuel efficient it's going to be. Once we know weight alone, we can explain 75% of the variation across this sample in miles per gallon, right? We can explain almost all of the variation in fuel efficiency across the sample if we only know the weight. Now, we can do better, right, by adding in the engine power, but it's a 7% gain, not that high, right? Now, with miles per gallon alone, we explained 60% of the variation, but when we added weight in, right, we got up to 82. That's a big jump. That's a 22-point jump. So what we're kind of seeing here is that weight alone, now, you know, we're looking at this and horsepower is minus 0.03, weight is 3.8 on the magnitude of those coefficients, but they're on really different units of measurement. So comparing those on their own doesn't make a lot of sense. But in terms of explanatory power, weight appears to be doing more work in terms of explaining miles per gallon than does engine power. And we could get that from R squared, right? It's explaining more of the variation in the outcome. Yeah, we'll keep going through this stuff as we go, right? But it's kind of introducing a lot today. And then we'll kind of keep building it out as we continue through the rest of the semester. But I'd like to practice fitting on another data set. So we've used the Gapminder data in homework before. Let's load it in again. You need to use the library Gapminder to load it in. And if it's not loading for you, just do install.packages Gapminder to install it. I'll confirm that I can load it on the console. And it's in. And let's look at this. Actually, I don't like to put head in my script. I like to put it on the console because I don't want it to render in my output. Okay, this is what's inside Gapminder. We have country, continent, year, life expectancy, population, GDP per capita. So what I'd like us to do is build a model for life expectancy. Based on the data we have. Now, of course, life expectancy is a function of all kinds of things, but again, we're building toy models that are just kind of abstractions of reality based on the data we actually have access to, right? So based on all this, how do we think? I'm identifying one predictor that I think would be a really strong predictor, one variable that I think would be a really strong predictor of life expectancy. What is it? GDP, right? GDP is the gross domestic product of a country per capita. So it's effectively the entire economic output of a country divided by the population size of that country, right? And so that is a relative indicator of the wealth of a country, right? The economic productivity of a country correlates to how much money the residents of that country have access to, right? Which should correlate with life expectancy for all kinds of reasons. If you have more access to money, you're likely to have better access to secure shelter. You're likely to have better access to food. You're likely to have better access to medical care, education, all that stuff, right? Okay, so we're going to say expected value of life expectancy is equal to a function of GDP per capita, right? And we're going to start with our simplest form of that model. Start with the simplest form of that model that we can think of, which would be a simple linear model between GDP per capita and life expectancy, right? So let's estimate that. Go ahead and estimate a linear model for life expectancy by GDP per capita. Just like so. Okay, so M1. Let's look at the summary. And what do we have here? What is that number? Anyone know what that number actually is? 7.6 E minus 04. Right, so that's 7.6 times 10 to the minus 4, which is equal to 0.00076. Right, we move 1, 2, 3, 4 decimals over, and we get 0.0007. So that's saying in practice that for every $1 increase in GDP per capita, we get a 0.00076 increase in life expectancy. Now, that seems really small. But is that actually a small relationship? I don't know. Let's see. Let's kind of So how would we know, what's another way we could think about this, to think about whether it's a small relationship or a big relationship?
Like, so like GDP is on a huge scale and life expectancy is on low.
So let's look at that. The minimum value for life expectancy is 23. The maximum value for life expectancy is 82. The minimum value for GDP is 241. The maximum is 113,000. It's a huge range, right? The range for life expectancy is about 60. The range for GDP is 100,000, right? So a 1 unit change in GDP is not very meaningful, right? It's a $1 change in country income per person. It's not a particularly meaningful difference, but a 1 year change in life expectancy is quite a meaningful difference, right? And one way we can think about that is by looking at the standard deviations of the data. The standard deviation for life expectancy is 12.9. So 12.9 year increase in life expectancy is the average deviation from the mean for each country in this data, right? Each country year, because these are repeated observations of countries. And the standard deviation of life expectancy, or of GDP, is 9,857. So we have really different scales here. So a few things we could do. The first thing to do is, if we think this linear relationship is really a good one, and we just want to get a better sense of the underlying relationship, well, the first thing we can do is what we've already done, is we can predict, right? So let's predict along the range of observed GDP. So we'll call it test data. This data frame where GDP per cap, and it needs to be spelled and punctuated exactly like it is in the observed data, because it's going to run it through predict. So it's going to look for a column that shares a name with the column from the observed data. We're going to do we're just going to run from the minimum of GDP per cap to the maximum of GDP per cap. It's not an integer. Oh, right. Gapminder, $, Gapminder. Let's just stay consistent. Instead of using colon, I'm going to do sequence. We'll sequence from the minimum of Gapminder to the maximum of Gapminder. And this time, instead of using length out, I'm going to use a different argument. One argument I can use here is from and to and by. So in this case, I'm going to say by, let's step by, I don't know, $50. So each step on our sequence is going to start at the lowest value of GDP, and it's going to go up to the highest value of GDP. And each value of it is going to be 50 points lower than the value that comes next. So instead of length here, I've set the step size, right? And I've set the step size to be equal to 50. And so how many rows is this going to have? It's going to have a lot. 2,266, right? Now, if I change this instead to length dot out 50, right, I can get a really differently shaped object. Instead of 2,266, I have 50 rows. And now our step size is going to be quite large. It's going to go up by like 2250 each step, right? So it depends on the shape of the object we want and the kind of question we're asking. I think by equals 50 is good here. Okay, so now we could do test data. We'll call it plot data, rather. Plot data is going to start from test data, and we're going to add on to it our predicted values. Y hat equals predict M1 new data equals test data. So now in plot data, I have an object that shows me for each GDP per capita ranging from the minimum and then up to the maximum with steps of 50, what's the expected value of life expectancy? So we can see here, going from a GDP of 241 to 291, life expectancy increases by 0.03, right? Also note here that life expectancy starts at 54 for the lowest value of GDP in the data. but the minimum value for life expectancy is like 21. Right? So already we know this model's not going to fit especially well, right? Because the minimum value of GDP is predicting a quite high value of life expectancy that's much higher than the minimum we observe in the data. So let's check this out though. Is this a big or small relationship? Difficult to say right now. We can't tell from the coefficients alone without thinking about the scale of measurements of our variables, right? So X equals GDP per cap, Y equals life expectancy. Let's do a geom line. Let's look at it. What's wrong? Oh, right. Y hat. Okay, now there's our model. Now, as we go from the minimum to the maximum, there's another problem with fit here. Anyone want to tell me the other problem with fit here? We were predicting way too high for our starting value. And what at the maximum values of GDP per capita in the data, what are we expecting life expectancy to be? 140? Yeah, that's clearly not correct, right? And that's because there's diminishing returns, right? That we can't infinitely increase life expectancy as a function of wealth, right? At a certain point, no matter how rich you are, you're still going to die, right? You can't keep increasing as much as, you know, Jeff Bezos would like to have us believe otherwise. You can't live forever, or all these other people talking about extracting blood and doing whatever kind of crazy immortality games they're doing. You can't live forever, right? So at a certain point, there's diminishing returns to wealth and income. But this is actually on this scale, you know, if we go up on the range, if we go from 0 to 30,000, we go from 50 to 75. And in the terms of a human lifespan, that's a big deal. 25 years of life expectancy, right? So if we go like a fourth of the way up between the minimum and the maximum, right? We get a huge gain in life expectancy. So I would call this a very large relationship. Now, clearly, we have a model misspecification. A misspecified model means it's producing nonsense, right? The model produces nonsensical inferences. 150 years, not possible. So that's nonsense. Yes, this model's wrong, right? All models are wrong. This one is especially wrong. This is both a wrong and useless model. But we wouldn't know that until we plotted it out, right? Okay. So one way to think, but now I just want to show you as an exercise. The point here is that when we look at these coefficients, 0.0007, you would look at that and say, that's really small. But it's actually really large, right? On the scale, if we consider the units of measurement of the data. Now, one way I can make my coefficient look big if the relationship is big is by using the scale function. Let's actually do that as in 2. If I scale life expectancy, and remember what the scale function does is it mean centers and then turns into, so it first subtracts the mean off. So the mean of this new variable will be 0, and then it divides it by its own standard deviation. So it converts every measure that we're putting in there onto the same unit. That is mean centered standard deviation 1. It's a linear transformation, so it's not going to change the underlying relationship in the data. But we're going to get really different coefficients. So let's look at this. M1 gave us 0.0007. M2 is going to give us 0.5. So on model 2, it's saying for a 1 standard deviation increase in GDP per capita, you get a half standard deviation increase in life expectancy. That's a big effect. Even though it looks 0.5 times, the way ours is displaying it, it's kind of gross, but that's a big effect. And it's going to look functionally the same. Let's compare those two plots. So I'll just switch out model 1 for model 2 in my plot data. And when we compare these two plots, it's identical. The shape. What's different is the axes, right? The scale of the axis here goes from 50 to 150. Scale of the y here goes from like -0.5 to 6. And now this is standard deviations away from the mean. Mean is 0, standard deviation below the mean, standard deviations above the mean, right? And why? Oh, because I've still got GDP on a weird scale. Never mind. Anyway, there's more I would need to do to make the plot work, but you could see that the underlying functional relationship between x and y is the same no matter what we do when we do a linear transformation on the variables, right? That is when we add or divide things simply, right? All we're doing is reshaping the axes. The basic functional relationship will remain the same. And so it can be quite convenient to look at model 2 instead of model 1, right? Because on model 1, we're looking at this and we're saying, well, 0.0007, I don't know. Is that meaningful? Is that big? Is that small? I have no clue. Model 2, oh, a standard deviation increase in x is a half standard deviation increase in y. That's meaningful, right? That's a meaningful association. So we can standardize the units to aid in our interpretation when we're just looking at the coefficients with the scale function. If we're visualizing, it doesn't matter. Because if we're visualizing, we can have it on whatever scale we want, and we can still see the underlying pattern. But let's take this a step further. Shoot, we don't have time to take it a step further. We'll take it a step further next time. Actually, I'm just going to give you a little preview because I'm really excited about it. Let's say that instead of, and we'll work through it in practice next time, instead of it just being a linear function of life expectancy, what if it's a logarithmic function of GDP, right? So what if that relationship is modeled as a logarithm? Let's introduce nonlinearities in. We're actually going to get, if we look at M3, we get a 65% R squared. And if we look at M1, we're going to get a much worse fit, 34% R squared. So the information we put in terms of our variables, GDP per capita, is the same across both models, but we applied a transformation to one of our variables, a logarithmic transformation, which implicitly assumes there's an exponential relationship between GDP and life expectancy. And once we did that, we get a much better fitting model. And I'll visualize it for you and show you how that works next time when we have kind of what's called a log linear model, right? But we can do transformations of our variables to improve model fit very dramatically when we have theoretical reason to suspect the relationship may be nonlinear, which a lot of times it is, which is most things. Lines are too simple for most processes. Okay, cool. Homework is posted. It's the mark of a criminal record, but instead of doing just comparing means, this time you're actually going to estimate regression models, and it shouldn't be too tricky. I've shown you everything you need to do. Just remember that you're using categorical predictors for the individuals, right? You're using the race and the criminal record are both binary categorical predictors, right? So it's 0, 1, 0, 1. So that question about what we're actually estimating is different intercepts, right? We don't actually have a slope in there, but so that's a little tricky, but you'll be able to manage it just fine. I'll get the Slack channel open today, and I'll also post this demo code for regression fitting. We'll keep working through this next week. All right.